All right. Thanks everybody for joining me today for today's webinar on learning to see how to gain control of a reactive situation. I'll preface this by saying that we're going to go through a small primer. There's a lot to cover, but by the end of it, hopefully you understand where I'm coming from. And with that, my name is Joe Anderson. I'm co-founder and COO of Reliability X. Got a lot of certifications, been in the industry for almost 30 years now. Been doing this for quite some time, and I appreciate everybody for being here. So who is Reliability X? Well, our goal at Reliability X is to be an empowerment company. Our goal is to empower people to be able to solve problems and execute and do things in a world-class fashion. So what we like to do is train up people and give them the ability to do so that we're not a cash cow sitting in your company for 20 plus years. We're proud to say that we have 2 CMRP of the Year award winners in Ramesh and George, probably the only company in the world to have that. We also wrote the book on reliability and maintenance best practices through Ramesh Gulati. We're also on the board of the ISO 55000 TC 251 committee that helps set the standard. In this past year, we won a solutions award for basically bridging the gap between operations and maintenance with our plant turnaround system. And we'll kind of cover some of that today as a part of learning to see. So again, I appreciate you guys being here. We do offer a lot of training. We just launched Allentown courses schedule through the remainder of the year. Every month we'll be doing some training there. We're getting close to doing training in Kansas City area and in Wisconsin. So we look forward to that. And here's our training schedule coming up in Allentown. So we'd love to have you in Allentown to sit through our courses and learn a little bit more about how to handle situations. All right. So to get to it, there's basically 3 ways to see. And what I mean by giving yourself the ability to see is currently, typically from a maintenance perspective, when you walk into an organization, they tell you, well, we have a maintenance problem. And the reason that they tell you you have a maintenance problem is because they have 2 buckets of loss, basically, which is unplanned downtime and planned downtime. And because their unplanned downtime is high, and they assume maintenance owns unplanned downtime, therefore we have a maintenance problem. The problem with that picture is you've lumped multiple loss types into 1 or 2 buckets. And in that unplanned downtime bucket, there's a lot of categories of loss that sit in that bucket. And yes, breakdowns is one of them, but there's 6 other major, big losses that can sit in that bucket. And what we find a lot of times is it's not really a maintenance problem. What we find is a lot of times it's minor stops and process failures, which I'll kind of talk about. But if we don't define our losses correctly and categorize them into the right buckets, how do we know what strategy to apply to what bucket of loss? When you just say unplanned downtime, it's so general and generic, there's really nowhere to focus. And so first thing we're going to start with is understanding your losses. So I'm going to cover OEE. Now I know across all industries, this isn't maybe the right tool. OEE is a tool. Yes, we use it as a metric, but that should be its secondary use. Its primary use is to identify your buckets of loss so you know where to focus and what strategy to implement in order to go after that opportunity. And so with that, though, in most industries, you do have losses, and a lot of the losses are similar. And so take that as principle as we go through this. So first thing, in manufacturing, there's what's called the 30 major losses. Now, if you look on the internet, it'll tell you there's 16. That's because since the late 60s, early 70s, when TPM was created, no one's taken the time with the information we have today to update anything. And so we teach OEE has 7 losses. You'll find on the internet the 6 big losses. We teach 7 big losses, and I'll get to that. And we've also expanded our loss buckets to 30 major losses, not 16. So because we have more information today and we know kind of some of these new buckets and things that exist or things that were lumped together that shouldn't have been, we have updated it. So if you look on the internet, like I said, we are the only ones that do this. So, but we teach that there's 30 major losses in manufacturing. Our big focus is on the right-hand side. Those are your equipment-related losses. And equipment-related losses are typically the largest loss buckets that are within a given facility. So that's why we focus there. And OEE and TEEP are your equipment-related tools that you use to identify your loss buckets. We do what's called a loss analysis. Typically, we go into organizations and we do an assessment of maintenance and operations combined with what we call a loss analysis, where we're analyzing your loss buckets and breaking them down into buckets. And what we have found is the majority of losses in a given plant, on average, is operational issues or design related issues. It's not a maintenance problem. But because, like I said, we generically say, well, we have a lot of unplanned downtime, therefore maintenance. Because we haven't defined what our losses are, we don't truly understand. And so it's easy to see a maintenance loss because the machine doesn't work. And so it's visible to everyone and they can't see it. But what they don't take into consideration are the 600 1-minute jams that you see every week, causing you 10 plus hours of downtime. What we talk about is the 1 30-minute breakdown and say, yeah, because we had this breakdown, we didn't hit our numbers, therefore maintenance. And what we need to do is become more intelligent and break down those buckets and be able to explain them in a way that people can understand. And what we find is maintenance downtime on average is about 3%. And so do we really have a maintenance problem? Now, maintenance contributes to some of these buckets because they don't have a robust strategy, but is it as big as we think it is? And I don't think it is. So with OEE, the goal is to identify and understand the 7 big losses. Like I said, we added one. You're probably used to hearing the 6, but there are 7. Okay. And it's broken down into 3 categories, which is availability, performance, and quality. And in the availability bucket, this is where we define our losses. You have setup and adjustment losses. This is a deviation from a planned downtime standard. For example, if you take mass break, let's say you take a mass 15-minute break, that 15 minutes is planned downtime. But if it takes us 20 minutes to get back to the line, then we have 5 minutes that wasn't planned for. That 5 minutes is unplanned downtime, and that falls in your setup and adjustment bucket. The same thing with changeovers. If you have changeovers, you have 45 minutes to do a changeover on the schedule. That's planned 45-minute downtime. If it takes you an hour to get through the changeover, then you have 15 minutes that was unplanned. Therefore, you're not producing units. That 15 minutes would fall in your setup and adjustment loss bucket. Then you have a breakdown loss. A breakdown loss, by definition, is any unplanned stop 10 minutes or more and requires a part to be replaced. Now, well, let's move on to process failures. And a process failure is any unplanned stop 10 minutes or more and does not require a part to be replaced. So if I look in your CMMS system and I say pull up all the work orders for the past week, and how many of those work orders have parts attached to it? What we have found is about 75% of those work orders where you responded to a call do not have parts on the work order, which tells you you have a process failure issue, not a breakdown issue. And so, process failures, what ends up happening in many, many organizations is the machine isn't running properly. So, they call maintenance out. And maintenance makes adjustments to a machine, never replacing components, just making adjustments. But what that tells us is that we have an operator issue. We haven't trained our operators to be able to overcome those issues. They don't know their machine well enough. Now, the caveat to that is, as a maintenance manager, I always required my maintenance mechanics to train operators. Maintenance people don't typically like that, but it doesn't matter. If you want to quit getting the calls out to adjust the machines, you need to train your operators. And you are skilled trades, therefore, you train operators. Now, so what we find again, a lot of times, and I'm sure many of you can relate, is that you get called out to make adjustments to machines. That is not maintenance downtime. Just because we called maintenance out there doesn't make it maintenance downtime. A maintenance downtime cause is when it breaks and the machine no working no more. Then I have to go fix it and replace parts. That's a breakdown. That is where maintenance is responsible. Okay. And so that's your availability bucket. In the performance bucket, you have speed losses and minor stops. Now, a speed loss is not your theoretical max. It could be, okay? But what happens is over time, because we have so many minor stops in our system, we slow down equipment. And the reason we slow it down again is to offset the number of minor stops. And then we designate that as our theoretical max. What we need to be looking at is our design rate. What was the line designed to run? Or what was this machine designed to run? You paid for a machine to run at a certain rate. Let's say it's 100 units a minute. It was designed for. Well, what we'll find is they'll set theoretical max at 80 and they'll still only hit 60. And so you have this hidden bucket of loss called speed loss. And the reason it's hidden is because we've slowed down the line to compensate for the number of minor stops that exist. Okay. And so in order to find the issues that you need to overcome the speed loss, you have to speed the line back up and you document the new losses. But we'll get to that. And then you have minor stops. And a minor stop is any unplanned stop 10 minutes or less, regardless if a part is replaced or not. If you can replace a part in under 10 minutes and get the machine running, that's an operator function. They should be able to do that, changing suction cups, things like that. Really simple maintenance tasks, right? And minor stops make up about 50% of loss on average in any given organization in manufacturing. Then you have your quality losses. You have startup rejects and in-process rejects. Some companies don't have startup rejects. For example, if you're in injection blow molding and you have to run the machine 30 minutes and heat it up and recycle all of that plastic, right? Those are startup rejects and they should hit your quality bucket. The goal is to identify opportunities. The problem is because we're a red-green society, we want our OEEs to look good. So we don't really document that. But some companies don't have startup rejects. Then you have in-process rejects. This means while you're running. So if a check wire kicks out, you've got to rework, you got to touch it again. It's not a right first time. And that's what your quality bucket is. It's about right first time. And so what OEE does is help you as you break down these 7 losses, understand where your major issues are. It breaks down that what we call the unplanned downtime bucket. into smaller chunks, and there's a different strategy for each one of these losses. And so we apply the strategy for that loss and make them go away. And so overall, what you're really looking at is your net good processing time versus your planned production time. And that's what OEE is. Now, as a metric, it's used to measure the time you're scheduled to run. There's a lot of arguments over whether changeovers and breaks and all this stuff hit your OEE. It does not, unless you don't come back on time from break or you don't hit your planned downtime for your changeovers, then that additional time would be unplanned downtime. But OEE is a metric against planned time to run. So anything that's planned down doesn't hit OEE. Okay. And OEE is a series calculation. For world-class metrics, availability needs to be at 90%, performance at 95%, and quality at 99%. And that'll give you 85% OEE, which is the defined world-class metric. Yeah. But honestly, I don't like using it as a metric. I use it as a tool. I want to identify my losses. Red is good. Red means opportunity. This is where I can fix things and make problems go away. And these are the things that I need to identify in order to get rid of some of the problems. So really quick, you start with availability. So whatever your planned runtime is, minus any of the downtime in those three categories: breakdowns, setup and adjustments, process failures, get pulled out, and you divide, and that gives you your percentage. For example, if we're scheduled to run 8 hours, no breaks, you rotate breaks instead of taking a mass break. All right, that's 480 minutes you're scheduled to run. If you have 60 minutes of breakdown and 20 minutes of setup and adjustment issues, you didn't get back from a changeover on time, for example, you would have 80 minutes of downtime. And so you take that 480 minutes minus the 80 minutes of downtime, that gives you 400 minutes over 480 minutes, or 83%. That would be your availability percentage. Okay. Now, to do this calculation, you take what's left, which is that 400 minutes, and it hits your performance bucket. So performance focuses on the causes of manufacturing that upset the design, which minor stops are considered idling. So if you think about a car, all right, a breakdown would be the wheel falls off. So I have to replace the wheel, right? But sitting in traffic, the car can still run, but it's just sitting in traffic. That's considered an idling stop, which is a minor stop, which means you can't achieve your possible speed. If the speed on the highway is 55 miles an hour and you're not achieving it, it's considered a speed loss. And minor stops are an idle stop, which is a form of a speed loss. Yeah. Now, to calculate the individual buckets, the first thing you need to do is calculate a speed loss. So if we know the design rate is 10 units a minute, and you actually set the machine at 9 units a minute, we have a 1 unit per minute speed loss. And so to calculate that, we take the design rate times the number of minutes left, and then the actual run rate times the number of minutes left, and we subtract. So we're converting these units to time, right? So we're losing 400 units in that leftover 4,000 or 400 minutes, which means we lost 40 minutes of production for speed losses. So we lost 60 to breakdowns, 40 to speed loss, and 20 to setup and adjustment so far. Then we have to calculate what's called net good processing hours. So net good processing hours, what that means is if you took out all the losses, that would be all the time that you ran at your design rate. Okay, that would be net good processing hours. The way you find that is your 10 units per minute times 480 minutes means that a perfect 100% OEE day, you would produce 4,800 units. And you take the total units that you produced, which let's say you produced 3,300. Okay, and you divide the two. What that means is 68% or 69% of your scheduled time you produced units, which means a straight 5.5 hours you ran. But that also means for 2.5 hours you were down. Okay. So if you take the 80 minutes of availability loss and the 40 minutes of speed loss, everything that's left is minor stops. Remember, that's total units produced, not good units produced. And I'll get to that in quality. That means every unit that was produced, whether it's reworked, rejected, doesn't matter. That counts. Okay. So it's everything. So everything that's left at that point is minor stops. So to do that calculation, we have 330 minutes of time left divided by the 400 minutes from above. That gives you 82, almost 83% performance. And we move on to quality. So quality is your good parts or units or widgets divided by the total units. So whatever you got out of the system that is sellable product divided by whatever you put into the system. For example, it could be pounds. We got 3,000 pounds out of the system, but we put 3,300 pounds into the system, which means we lost 300 pounds in the quality bucket. Okay. The way you calculate that, good units produced divided by total units produced. So for example, 3,000 good units, we put into the system 3,300 units, which means our quality percent is about 91%. To be world class, your availability bucket needs to be at 90%, your performance bucket at 95, and your quality bucket at 99. And if you do the multiplication, 90 times 95 times 99, that gives you 85% OEE. Now, from the examples that we share, if we take those numbers and compare them, we need to be 90% on availability. Well, we're about 7% off. In performance, we're at 83%. We should be at 95%. So we're about 12% off. And at quality, we're about 8% off. Okay. So that kind of tells you a picture where your losses are and what's eating your lunch. Well, which one of these buckets, if you're comparing it to world class, getting each bucket to world class, what area would you focus on? And if I have almost 13% loss in my performance bucket, then that's the area I'm going to focus on. The problem with that is the performance bucket isn't a maintenance problem, but we think it is. So what this does is it gives us the ability to see. The answer here would be performance. So if we broke down our losses, and let's just say setup and adjustment losses annually, we had 100 hours. Breakdown losses annually, we had 200 hours. Process failures, 600 hours. Minor stops, 100 hours. Speed loss, 100 hours. Minor stops, 1,200 hours. And 25 hours of in-process rejects. This now starts to give you the ability to see what's eating your lunch. So where would you focus here? Do you have a maintenance issue? A small one, yes. But if I lumped all this together, you're looking at, 2,000 hours of loss a year. That's on planned downtime. And if all we're saying is unplanned downtime, how do you go about attacking it? And you can't if you've done nothing to give yourself the ability to see what's actually eating your lunch. And so by doing a simple loss analysis, you can understand where you should focus and start going after these losses and solutioning them and making them go away. And so this is kind of your first tip on giving yourself the ability to see. So let's cover quickly some strategy on how to go after some of these losses. Okay. So with setup and adjustment losses, a lot of times just get back from break on time. What we find in a lot of facilities is they'll run 2 10-hour shifts. They'll take 2 15s and a 30, and they become 2 20s and a 40 twice per day. And so now you're losing 40 minutes per day in production just because we don't come back from break on time. Well, if you extrapolate that out over a given year, you're losing $1 million just because we didn't come back from break on time, or more a lot of times, just because we couldn't get back from break on time. You also have, if you have a lot of changeovers, you might need to do a SMED, single minute exchange die. Figure out how you can streamline your changeovers and make them more consistent so that you get them done on time. And maybe you can shrink that time. Instead of needing 40 minutes, maybe you only need 20. That gives the business back 20 more minutes to run. And so if you could give, after, say, every other changeover, and if you do 4 changeovers a day, there's 40 minutes in production you can give back to the plant. So get back from breaks on time and get your changeovers done on time. You're looking at almost 2 hours per day of production that you get back. Very easy. Okay. With breakdowns, you need a robust maintenance strategy. Do you have a criticality analysis? You need to know how critical your equipment is. Just because you have a lot of production downtime doesn't make that asset critical. There's a lot more criteria. What if you don't have electricity? You shut your whole plant down. Is that more critical than a single line going down when you have 15 lines in the plant? So, should we ensure that our facilities are taken care of? What if you don't have an air compressor? There are things that are more critical than just production related downtime. Typically, your B ranked assets are going to be your highest downtime assets because those are your production assets. And so, how critical is it? Do you have an equipment strategy down to the failure modes? What failure modes are you addressing? Do your PM tests specifically address failure modes, or is it check the chain? If it's check the chain, what is the failure mode you're trying to address? It's not specific enough. It's an opinion or subjective. Okay. Implement PDM. Implement precision maintenance. And implement defect elimination. This will help you get rid of a lot of your breakdowns. For process failures, it could possibly be a redesign issue. For example, if an operator's out on the line and his butt accidentally hits an e-stop, and now we call maintenance out because we can't figure out why the whole line shut down. And 20 minutes later, we figure it out. Somebody hit the e-stop. We pull the e-stop out, reset the machine, and start the line again. Well, we were down for 20 minutes. Okay. But we didn't replace a part. That's a process failure. But it could be that we need to relocate that e-stop. Nobody's butt should hit an e-stop and shut the line down. Now, there's ways you can overcome that, but it might need to be relocated, raise it up just a little bit. Some of it could be center lining issues. Expose bad materials or expose certain specifications that aren't set up on the machine. So it could be center lining. Again, that's an operator function. Or it could be just operator training. Maintenance is always out making adjustments to machines. Maybe we need to train our operators. This will help you eliminate process failures, and process failures are the second largest loss bucket on average in a manufacturing facility. And so it's a good one to go after, and it's fairly easy, fairly cheap. Then you have speed losses. So speed losses, the inverse of a speed loss is a minor stop. What ends up happening, like I said before, is you get a lot of minor stops. So we slow the line down until it's bearable. Then when it's bearable, we say, well, that's the fastest this line can run, because we never solutioned all those minor stops. Now, I would recommend going after speed losses later as you get other minor stops out of the system. But when you get to a point where you're fairly stabilized and good, you can start playing around. Go out for an hour, speed up the line to its design rate, and see what new issues creep up. And when those new issues creep up, document them as thoroughly as you can, then slow the line back down and allow them to run back at that speed, and then figure out ways to solution those newly surfaced issues. If you don't overcome those issues, you're never going to overcome the speed loss. With minor stops, a lot of times it's underlining or clean and inspects. What we found at one client here, over the summer, is there was a jam. One of their major jams was costing them 10 hours of downtime per week in production. And all it was that the belt was getting dirty. And it's a washdown facility, but product was getting all over the belt and was jamming up product on a reject. And so what we did is we added to their CIs, their clean and inspects, to every time before they go to break, because they took mass break, to clean that belt. And they cleaned the belt, and that minor stop went away, gaining 10 hours of production per week across 2 shifts. And so their OEEs went from the lower 40s to the mid 60s pretty much overnight, because we solved one issue. Okay. And then you might need to make some modifications, but you really need to be out there solving problems. The problems aren't in a meeting. The problems are out on the floor. So if you're going to have a bunch of meetings, you have the meetings out on the floor to solve problems. Meetings don't make your problems go away. Meetings are a way to look busy. Nothing gets accomplished in meetings. Results. What results have come out of a meeting? Results come from going out to the floor and making the issues go away. Grab 2 mechanics, grab a good operator, grab your CI or OPEX person, grab your safety person. Make them all go out with you at 9 o'clock on Tuesday morning. We're going to go solutions and problems out on this line. That's our meeting. For 2 hours, we're going to spend time out here just observing. And then try to solution the problem out there on the floor. What do you think we could do to fix it? Well, I've been telling people we should do this and that. You're going to hear all the solutions when you actually interact with the people. And then you go out and you try to implement them. Well, what do we need to do? Help me understand. What can I do to help? What obstacles do I need to remove? Let's make it go away. What do we need to do? Results come from execution. They don't come from a meeting. So be out on the floor solving problems. So that's number 1. The next 2 are fairly quick, but they're optimal, especially when it comes to maintenance. And the first one is asset health monitoring. What asset health basically is the number of defects you have in the system divided by the number of assets. And your goal is to be in the 90% area of asset health of defect-free assets. 95 better. Okay. But at first, it's probably not going to work. But you look at a chart kind of like this. Green is good. That means the percentage of assets without defects. And red means opportunity, number of assets with defects. This gives yourself the ability to see, what's my asset health? Well, I know I have a lot of defects. Well, we need to get these defect solution. So let's get parts ordered, plan and schedule the work. Let's kit the jobs and go execute the work. What we do a lot in maintenance, because we don't truly understand it, is we spend our downtime, our scheduled downtime, doing what we call PMs. The problem with that is our whole weekend gets ate up doing PMs, and we never do the work to correct the defects that exist in the system because we're doing inspections all the time. PM should be inspection unless it's a time-based rebuild. You should be inspecting for defects and writing up follow-up work orders so that you can plan and schedule the work and go execute, get rid of the defect. But we spend so much time doing what we call PM. Well, most of our PMs should be done while we're running. The problem is you have to set up your equipment to give yourself the ability to do inspections while you're running. You have to have the tools to do inspection while you're running. But what we do is we spend all of our planned downtime doing these PMs and none of the defects get out of the system. And then we just create this vicious cycle. Well, I'm doing PMs. Well, nothing's running on Monday morning. Well, I wonder why. Not only did we not get defects out of the system, but we readjusted all the equipment because we were playing around doing PMs, not knowing what we're doing. And we put more defects into the system because we don't understand precision maintenance. And so we end up in this vicious cycle, which isn't a good place to be. You have to set your equipment up to be able to do things while you're running. You're supposed to lubricate while you're running. How many of you do lubrication while you're running? How many of you are using ultrasonic assisted lubrication so that you're putting the right amount of grease in at the right time? Right? So there's a lot of things that you have to do to set yourself up for that, but that's what we should be focused on in maintenance, to be able to do our inspection while we're running. Like I said, unless it's a time-based rebuild, then we're touching the machine. If you're touching the machine replacing parts during a normal PM, that's called corrective maintenance. That's not preventive maintenance. So you've left the realm of PM and you're doing corrective maintenance. Oh, this chain needs to be replaced. Let me go grab a chain. I go try to find a chain. I can't find the chain. Oh, I found a piece of a chain. Well, let me lump a couple pieces together. We'll throw this new chain on. And now our whole day's gone. And the only thing we did was replace the chain, and we didn't even do it with precision because we didn't have the parts. And we wonder why we're in the situation we're in. So give yourself the ability to see how many defects do you have in the system versus the number of assets. What's my asset health look like? This tells you, look, I got a problem. If you're not in the 90%, somewhere up between 90 and 100, you need to focus on getting defects out of the system. And maybe PM isn't the right approach. Because if anything, a lot of us are putting more defects in when we do what we call PM. But that's a whole nother webinar to go through that. So why don't you do this? Create a requirement for mechanics to put in 10 work orders from defects they found walking around the plant. Now, your planner isn't going to like that a lot, and your backlog's going to grow. Typically, when we do these exercises, you'll find 1,000+ defects within the first few weeks. So you're inundated with work orders or work requests, which stinks for a planner. But the goal then is to get as much of this work scheduled to get out of the system. The more you can restore your assets, the better they're going to run. If we're always inspecting them and not restoring them, which means you're technically not doing maintenance, you're doing repair. The word maintenance in and of itself is defined as proactive. It means to guard or protect, to keep from failure. The act of maintain means to guard or protect. That is maintenance. Once a defect is initiated, you're no longer in the realm of maintenance. And we say, oh, it's reactive maintenance. Reactive maintenance is a self-contradictory term. How can you react to something that you're guarding or protecting? Which means something's already failed or it's in a failed state, which means you haven't maintained base condition. Therefore, you're no longer doing maintenance. You're doing repairs. That's why it's called, your storeroom is called maintenance, repairs, and operation. You have maintenance, which is the stuff you're doing to keep defects out of the system. And then you have repairs. So once you leave the realm of defect free, you're no longer doing maintenance. It's repair. So have mechanics put in 10 work orders a week. After 4 to 6 weeks, you'll actually have a backlog and you'll have some stuff you could plan and schedule. Keep track of the number of defects found and the number solution. And share it with people. Hey man, we found 1,000 defects, but we only solutioned 10. By solutioning 10, it's not really going to get us anywhere. So we need to step that up. What do we need to do? Help me understand. What do I need to do? What can I do to help? What obstacles do I need to overcome? Yes, your maintenance budget's going to suffer a little bit up front, but it is regardless. Your assets are going to determine your maintenance budget, not finance, not the plant manager. Your assets will. If you don't get an effective maintenance strategy, it's going to go down, and now it's going to cost you 4 to 10 times more to do maintenance on it. And so your assets don't care what your finance manager thinks or your plant manager thinks. It's going to go down when it goes down if we're not taking care of it. Okay. Now, this also, when you start to see where your defects are, gives you the ability to see, which means I can start to take control. Proactivity means you control the asset. Reactivity means the asset controls you. The goal is to be proactive. Okay. And so as you start to find all these defects, you can start to see where all your problems lie. Okay. Now, the next one is the use of PDM technologies. With the use of PDM technologies, well, let me rephrase that. It is not possible to be successful in maintenance without PDM technologies. It's not possible. A lot of people think it's an option or a nice to have, and that is just untrue. It's a must have. You cannot be successful without these technologies. Let me share with you an example. So PDM now you have condition monitoring, which is a little different. PDM sits in the bubble of condition monitoring. Okay. But PDM, typically, when we talk about PDM, we're talking about 5 technologies: vibration analysis, ultrasound, infrared, oil analysis, and motor circuit analysis, or electrical signature analysis. Okay. But if you and I walk into your plant and I say, hey, let's go look at some equipment, and we walk up to this conveyor. It can be any piece of equipment. Okay. But for this example, let's just say we walk up to this conveyor. And I say, hey, man, tell me what's going to fail next. And you say, what do you mean? I'm like, tell me, like, this conveyor's running. Tell me what on this conveyor is going to fail next. You're going to look at me like I'm crazy. But this is the problem, is because we haven't given ourselves the ability to see, we don't know what's coming. We don't truly know what the condition of this conveyor is. But if I'm using PDM technologies and I have routes set up, let's just say I'm using ultrasound and I'm using oil analysis. I'm pulling an oil sample on this gearbox, and my bearings I have set up on an ultrasound route. Okay. And I walk out and I ask you what's failing, and you say, well, based on this oil analysis report, it looks like the gearbox is starting to fail. It's becoming yellow, which means something is starting to go in the gearbox. And you have this ultrasound route set up for all your bearings. You have a baseline. You've taken your baselines, and every month you're going out and doing your route. And this month, one bearing here up in the corner is at 38. Well, the rule of thumb is 8 to 12 rise in decibel level means the bearing needs lubricated. That's great. So I'll take my ultrasonic grease gun caddy, lubricate this bearing, and bring it back down to its baseline. But then over here in this gearbox, let's say, we have this bearing that's at 57 decibels. Well, 16 plus rise in decibel typically means that you have a bearing that's failing, which probably coincides with that oil analysis report and what is failing in the gearbox. So by setting up these routes, and now we walk out to this conveyor and I say, hey, what's failing? And you say, well, actually, that gearbox has a bearing that's going out. We've ordered the gearbox. So when it's come in, we're going to replace it. Now you've taken control of the asset. You've given yourself the ability to see. I know where my problems are and what the strategy is to go after it. And this keeps you on top of your game and keeps the equipment maintained. And this is what I'm talking about when it comes to learning to see. I need to know where my plant losses are. It can't be one general lumped bucket. There's multiple losses in that unplanned downtime bucket, and there's a different strategy to go after those. I need to understand how many defects I have in my system, and I need to understand where they are. Those are the three things you need to give yourself the ability to see so you can take control of the situation and do something about it. Okay. So with that, a focus on learning to see, if you focus on those three things, you'll definitely lower your costs. When things don't break, how much money do you spend buying parts? When things don't break, how much more units do you produce for the same amount of labor? Which means your cost to produce goes down. Being more reliable costs less money and makes you a lot more money. Let alone, it's a lot more safe. You produce higher quality product. I know it's counterintuitive, but it's actually true. When things don't break, I don't have to buy parts. I don't need to store parts. When I can find defects early enough, I can order my part from the OEM or from a supplier. I don't need to stock it on my shelf, reducing my overhead costs that way. So it's a win-win-win-win situation by giving ourselves the ability to see. Thank you guys for joining me. I appreciate you being here for this webinar. If you would, there's an evaluation QR code here. If you scan that QR code, it'll take you to a link to evaluate this webinar so you can give us feedback on whether it's, Joe's a sad presenter, or I would really like some information on some other topic so we can form webinar around that. We do webinars weekly, so join us every Thursday at 11 Eastern time. We do webinars on different topics. We would like feedback. What would you like to hear? What would you like us to teach about, or find a new presenter or whatever? Use the webinar code 2024_5. That'll be the evaluation form for this webinar. If you do that, check out our website at reliabilityx.com. We have all of our events, upcoming training, a lot of resource materials a lot of downloadables, things like that. We also have a YouTube channel. We have a podcast, Practical Reliability Podcast, and the Reliability Experience on YouTube, where we cover a lot of things. You might check those out. Subscribe to us. We appreciate that. If you have any questions for me, send me an email, joseph.anderson@reliabilityx.com, and check out our column in plant services called Captain Unreliability, where we get to poke some fun at the industry. And with that, I appreciate you guys being here today. Have a great weekend.